The National Electrical Code (NEC) does not contain a specific section mandating the use of red concrete in duct banks. However, it's important to understand what the NEC does require regarding duct bank construction. Section 356.20 of the NEC addresses the construction of underground installations. This section stipulates that duct banks must be constructed of approved materials. These approved materials must be resistant to corrosion and physical damage. The term approved generally means acceptable to the authority having jurisdiction, often a local building inspector or electrical inspector. The selection of appropriate materials for duct banks is crucial for ensuring the long-term integrity and reliability of the electrical system. Corrosion can significantly weaken the structure and lead to system failures, while physical damage can compromise the conduits and cables within. Red concrete is frequently employed in duct bank construction, although not explicitly mandated by the NEC because of its inherent properties. Firstly, red concrete is known for its strength and durability. It provides a robust encasement for the electrical conduits, protecting them from external forces such as soil pressure, vehicular traffic, and ground movement. Secondly, unlike standard concrete mixes, red concrete typically does not contain iron. This absence of iron is a significant advantage in underground applications. Iron is susceptible to corrosion, especially in damp or chemically aggressive soil environments. The corrosion of iron within concrete can lead to spalling, cracking, and ultimately, the degradation of the entire duct bank structure. Because red concrete is iron-free, it mitigates the risk of corrosion-related failures, extending the lifespan of the duct bank and reducing maintenance requirements. While the NEC doesn't explicitly require red concrete, it does mandate the use of materials that are resistant to corrosion and physical damage. Red concrete often fulfills these requirements due to its durability and lack of iron. The choice of materials for a duct bank should always be based on a thorough evaluation of the site conditions, including soil composition, moisture levels, and potential exposure to chemicals. Consulting with a qualified electrical engineer or contractor is recommended to ensure compliance with all applicable codes and standards, and to select the most appropriate materials for the specific application. In summary, while the NEC does not specifically mandate the use of red concrete in duct banks, its use is a common and often preferred practice due to its durability and resistance to corrosion. The NEC emphasizes the importance of using approved materials that can withstand the environmental conditions to which the duct bank will be exposed. It is the responsibility of the designer and installer to ensure that the selected materials meet these requirements and provide a reliable and long-lasting electrical infrastructure. Always refer to the latest edition of the NEC and local codes for the most up-to-date requirements. Additional considerations beyond the NEC requirements include the thermal properties of the concrete used in duct banks. The thermal resistivity of the concrete affects the heat dissipation from the conductors within the conduits. Higher thermal resistivity can lead to increased conductor temperatures, potentially dirtying the ampacity of the conductors. Therefore, the selection of concrete should also consider its thermal characteristics, especially in high current applications. Furthermore, the installation practices for duct banks are also critical. Proper compaction of the concrete around the conduits is essential to ensure uniform support and prevent voids that can compromise the structural integrity of the duct bank. The spacing between conduits should also be carefully considered to allow for adequate heat dissipation and to prevent mechanical interference. When designing and installing duct banks, it is important to consider the potential for future expansion. Provisions for adding additional conduits should be incorporated into the design to accommodate future load growth. This can be achieved by oversizing the duct bank or by providing spare conduits. Another important consideration is the identification of duct banks. Duct banks should be clearly marked to indicate their location and the voltage of the cables they contain. This helps to prevent accidental damage during excavation or other construction activities. The marking should be durable and easily visible. Regular inspections of duct banks are recommended to identify any signs of deterioration or damage. Inspections should include visual examination of the concrete for cracks, spalling, or other signs of distress. If any problems are detected, They should be addressed promptly to prevent further damage and potential system failures. In addition to the NEC, other standards and guidelines may apply to the design and installation of duct banks. These may include local building codes, utility company requirements, and industry best practices. It is important to be familiar with all applicable requirements before beginning any duct bank project. In cold climates, it is important to consider the effects of freezing and thawing on duct banks. The expansion and contraction of water within the concrete can cause cracking and spalling. To mitigate this risk, air-entrained concrete should be used. Air-entrained concrete contains microscopic air bubbles that provide space for the water to expand when it freezes, reducing the stress on the concrete. Also, proper drainage should be provided to prevent water from accumulating around the duct bank. In areas with high water tables, it may be necessary to install a drainage system to keep the duct bank dry. The drainage system should be designed to effectively remove water without compromising the structural integrity of the duct bank. The design of duct banks should also consider the potential for seismic activity. In earthquake-prone areas, the duct bank should be designed to withstand the anticipated ground motion. This may involve using reinforced concrete and providing adequate support for the conduits. The seismic design should be performed by a qualified structural engineer. When working with concrete, it is important to follow proper safety procedures. Concrete can be irritating to the skin and eyes, so it is important to wear appropriate personal protective equipment such as gloves and safety glasses. Concrete dust can also be harmful if inhaled, so it is important to wear a respirator when working in dusty conditions. Always follow the manufacturer's instructions for mixing and handling concrete. Improper mixing or handling can result in weak or unstable concrete. When placing concrete, it is important to ensure that it is properly consolidated. Consolidation removes air pockets and ensures that the concrete is in full contact with the conduits and the surrounding soil. Consolidation can be achieved by vibrating the concrete or by using hand tools. After the concrete is placed, it must be properly cured. Curing involves keeping the concrete moist for a period of time to allow it to fully harden. Curing can be achieved by covering the concrete with plastic sheeting, burlap, or other materials that will retain moisture. The curing time will depend on the type of concrete and the ambient temperature. In summary, while the NEC doesn't dictate the color of concrete, it sets performance standards. Red concrete's properties often make it a suitable choice, emphasizing the importance of material selection for corrosion resistance and durability. The overall design and installation should always adhere to best practices for long-term reliability and safety, considering factors beyond the specific color of the concrete. Always consult the latest edition of the NEC and relevant local codes for complete compliance. The selection of the proper type of concrete for a duct bank also involves considering the soil conditions. If the soil contains sulfates, for example, it is essential to use sulfate-resistant concrete. Sulfates can react with the cement in concrete, leading to expansion and cracking. Sulfate-resistant concrete contains special types of cement that are less susceptible to sulfate attack. Another factor to consider is the presence of chlorides in the soil. Chlorides can accelerate the corrosion of reinforcing steel in concrete. If the soil contains chlorides, it is important to use concrete with a low chloride permeability. Low chloride permeability concrete will help to protect the reinforcing steel from corrosion. The design of the duct bank should also consider the type of cables that will be installed in the conduits. Different types of cables have different ampacity ratings and heat dissipation characteristics. The design should ensure that the cables can operate within their rated temperature limits. This may involve selecting conduits with adequate diameter and spacing to allow for proper heat dissipation. The design should also consider the voltage drop in the cables. Excessive voltage drop can lead to reduced performance of electrical equipment. The design should ensure that the voltage drop is within acceptable limits. This may involve selecting cables with larger conductors or reducing the length of the cable runs. The grounding and bonding of the duct bank are also important considerations. The duct bank should be properly grounded to provide a low impedance path for fault current. This helps to protect personnel from electric shock and to prevent damage to electrical equipment. The conduits should be bonded together to ensure that they are at the same electrical potential. This helps to reduce the risk of arcing and sparking. The design of the duct bank should also consider the potential for future maintenance and repairs. The duct bank should be designed to allow for easy access to the conduits and cables. This may involve providing access points at regular intervals along the duct bank. The design should also consider the potential for future upgrades or modifications. The duct bank should be designed to allow for the addition of new conduits or cables without disrupting existing services. The documentation of the duct bank is also important. Accurate records should be kept of the location of the duct bank, the materials used in its construction, and the type of cables installed in the conduits. This information will be valuable for future maintenance and repairs. Regular inspections of the duct bank should be performed to identify any signs of deterioration or damage. The inspection should include visual examination of the concrete conduits and cables. Any problems that are detected should be addressed promptly to prevent further damage and potential system failures. In summary, the design and installation of duct banks require careful consideration of a variety of factors, including the NEC requirements, soil conditions, cable types, grounding and bonding, maintenance and repairs, and documentation. By following best practices and consulting with qualified professionals, it is possible to ensure that the duct bank will provide a reliable and long-lasting electrical infrastructure. Remember to always consult the latest edition of the NEC and relevant local codes for complete compliance. This detailed planning and execution helps to protect the public's safety and the property of others. The concrete encasement of buried electrical ducts serves several critical purposes beyond simply providing a physical barrier. It protects the buried cables from mechanical damage due to digging, soil movement, or the weight of traffic above. The concrete also helps to dissipate heat generated by the conductors within the ducts, allowing for higher current carrying capacities. In addition, the concrete provides a stable and uniform environment for the ducts, preventing them from shifting or settling over time. The type of concrete used for duct banks should be carefully selected based on the specific site conditions. As previously discussed, sulfate-resistant concrete is necessary in soils with high sulfate content. In areas with freeze-thaw cycles, air-entrained concrete is essential to prevent cracking and spalling. The concrete mix should also be designed to achieve the required strength and durability. The compressive strength of the concrete is an important indicator of its ability to withstand loads. The durability of the concrete refers to its ability to resist deterioration from environmental factors such as moisture, chemicals, and abrasion. The installation of the ducts within the concrete encasement is also critical. The duct should be properly aligned and spaced to allow for easy cable pulling. The ducts should also be securely supported to prevent them from shifting during the concrete placement. The concrete should be placed in layers and thoroughly consolidated to eliminate air pockets. The concrete should be cured properly to achieve its full strength and durability. The backfilling of the trench after the concrete has cured is also important. The backfill material should be carefully selected to provide adequate support for the concrete encasement. The backfill should be placed in layers and compacted to prevent settling. The surface of the trench should be graded to prevent water from ponding above the duct bank. The marking of the duct bank is essential to prevent accidental damage during future excavation. The location of the duct bank should be clearly marked with warning signs or buried markers. The markers should indicate the presence of buried electrical cables and the voltage of the cables. The markers should be placed at regular intervals along the duct bank and at all points where the duct bank changes direction. Regular inspections of the duct bank are necessary to identify any signs of damage or deterioration. The inspections should include visual examination of the concrete ducts and markers. Any problems that are detected should be addressed promptly to prevent further damage and potential hazards. The design and installation of duct banks should be performed by qualified professionals with experience in underground electrical construction. The design should comply with all applicable codes and standards, including the NEC and local building codes. The installation should be performed in accordance with industry best practices. In addition to the technical aspects of duct bank design and installation, it is also important to consider the environmental impacts. The construction of duct banks can disrupt soil, vegetation, and wildlife habitats. The use of concrete can contribute to greenhouse gas emissions. The disposal of waste materials from the construction site can pollute the environment. To minimize the environmental impacts of duct bank construction, it is important to use sustainable construction practices. These practices include minimizing soil disturbance, using recycled materials, reducing waste generation, and controlling pollution. The long-term performance of a duct bank depends not only on the initial design and construction, but also on ongoing maintenance and monitoring. Regular inspections should be conducted to identify any signs of deterioration, such as cracks in the concrete, corrosion of the conduits, or damage to the warning markers. Any identified problems should be addressed promptly to prevent further damage and potential hazards. The maintenance program should also include periodic testing of the electrical cables within the ducts to ensure that they are functioning properly and that there are no signs of insulation breakdown. The testing should be performed by qualified professionals using appropriate equipment. The results of the testing should be carefully documented and used to inform future maintenance decisions. In some cases, it may be necessary to replace the electrical cables within the ducts. This may be due to age, damage, or the need to upgrade to higher capacity cables. The replacement process should be carefully planned and executed to minimize disruption to electrical service. The old cables should be disposed of properly in accordance with environmental regulations. The design and installation of duct banks is a complex process that requires careful attention to detail. By following best practices and consulting with qualified professionals, it is possible to ensure that the duct bank will provide a reliable and long-lasting electrical infrastructure while minimizing environmental impacts. Always remember to consult the most recent version of the NEC and all applicable local codes to ensure proper design and compliance.